Okay, people, today we're going to go on to topic 12.1. It's going to cover quite a few interesting subtopic I would say. But the first of all the subtopics I'm going to go through is this thing called the photoelectric effect. It is that effect that won Albert Einstein his Nobel Prize, even though he is actually much better known for theory of relativity. E equals to mc squared. Exactly. You go to Kopitiam uncle, don't be surprised. Some Kopitiam uncle can tell you. You ask him, do you know Beethoven? You know. Dun, 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 dun. You ask him whether you know Einstein. Yeah. E equals to mc squared. So that equation is so well known by people. Even those who are not in physics, they can tell you that E equals mc squared. So that's actually a much more powerful equation. But the unfortunate thing about theory of relativity is that it cannot be proven without doubt. It can't. It just can't. In order to be proven without doubt, you need to perform experimental procedures to verify in the lab. And there's no way you can create a mass big enough in the laboratory without creating a black hole that will eat everyone up. So the thing is that's why they cannot experimentally prove it without doubt. That's why he didn't get the Nobel Prize for theory of relativity, unfortunately. But still, he's a genius who actually found his way through the other path, which is the photoelectric effect. Now, the reason why photoelectric effect is really a big thing is because it fundamentally changed the way we look at light. Before Einstein, everyone looked at light as four-letter word starting with W. Waves, exactly. So everyone thought that light is a wave, and they rightfully think so, because light, which is a wave, goes through all the wave phenomena, diffraction, interference, all these things. You don't expect two particles to knock into each other to become a bigger particle, right? Right? I mean, you don't expect proton to become a super proton. You just don't. Neutron, super neutron, you don't. But whereas waves come together, they can have constructive and destructive interference. So what Einstein realized is that, in fact, he wasn't even the one who discovered that effect. It was someone else. He was the one who interpreted the effect as an evidence for light being a particle. So what's the moral of the story? You need not be the person who does the hard work, but you can be the person who actually does the hard work in another way to interpret the experimental outcome and take Nobel Prize. The person who discovered the effect didn't get Nobel Prize there. It's like, yeah, the person who actually interpreted the experimental outcome. You just take the E and reinterpret. You wish. You wish. Turn it in 95%. Only the conclusion change. Then you probably, hopefully you get the Nobel Prize, but I'm sure that you won't get an IB diploma. Okay, so yeah. And so what did Einstein, what was the line of thought? You need to know the line of thought. So the effect, basically, photoelectric effect is the ejection of electrons from a metal surface when EM radiation of sufficiently high, this is important frequency, sufficiently high frequency is incident. Oh, this whiteboard is cleaner than usual actually. Yeah, it's actually quite clean. Okay, so it's the ejection of electrons from metal surface. Now, why metal surface? There is the thing recording. It is recording, right? Okay. So why from a metal surface? Make a guess. Why not from plastic surface or wood surface? Exactly, they're free electrons, and it is easier to eject electrons from those surfaces. It is possible to eject electrons from any surface if you actually have EM radiation of energy high enough. You just whack cosmic rays or whatever. Yeah, it will eject electrons eventually. So, but the thing is that you must remember that this was done about 100 years ago. So at that point of time, they don't have that kind of switch on high energy machine kind of thing, high energy particle. They don't have free access to high energy particles. So they use visible light, and the only material that can eject electrons using visible light are metal surface. Yeah, zinc, all these kind of metals. So that's why metal surface. And very importantly, sufficiently high frequency. Now let's take a look at what's the observation of this this effect. So what they would expect to see if light were to be a wave are these three things. These three observations are. Now, if intensity is high enough, then ejection occurs, regardless of frequency. Now, this absolutely makes sense if you think of light as a wave, because if I shine a very powerful beam of red light, then we got a powerful beam of blue light or whatever, so long as it's powerful enough, it should eject electrons, right? Intense what? A lot of energy, so electrons come out. If I were to shine a blue light, but very dim blue light, shouldn't have ejection because I'm sending less energy. Make sense? Now, the K of the electron depends on the intensity. which again makes sense. If I send in a lot of energy, then it should kick electrons out with more energy. Less intense, less energy. Now the third one is if intensity is low enough, you will expect ejection to happen only after some time. No need to copy this, I think this is in your notes. So the thing is that, but if copying helps you formulate your thoughts, then by all means. So these three observations are what you expect if light were to be a wave. Now the last one is quite common sense as well, because say for example, if you earn $1,000 a month, well, I don't know why you earn so little, but in the future I'm sure you earn probably, for some of you, 10 times or 100 times of that. So the thing is that if you earn $1,000 a month and you want to go to, say for example, like me, Antarctica for a race, the registration fee alone is about $20,000. So you need to save up a long time before you can go for your dream trip, right? But if you earn a lot of money, then you actually need to just save up for probably a month to go for a trip. So the same thing, if you have low intensity, it means that you need to store enough energy, wait for some time before the electron can hop out. Okay? So it makes perfect sense for these three if light were to be a wave. Guess what? Guess what? What was observed is in direct contradiction. Exactly, it's direct contradiction. So this is actually physics thinking. This is science thinking. You predict and then you observe, and hopefully you don't find what you predict. Because if you don't find what you predict, congratulations. This is an opportunity for you to have a job. You know, for you to come up with for you to come up with theories to explain, and then probably you can sign a 3-year contract or 5-year contract. For those 3 years, 5 years, you have a job secured. But if everything is as predicted, then why would the university need you to research? Nothing really, right? So sometimes if you find something that is not what you predicted, you should be happy. Yeah? Not those kind of, you draw the straight line, you plot the points, and you come up with the data kind of. Sounds... sinusoidal, yeah, of course. So what they observe is totally different. What they observe is this. They observe that if the frequency is too low, no ejection, no matter what you use the intensity to be. You use a super intense red light, doesn't eject means doesn't eject, but you use a very dim blue light, very, very dim blue light, it ejects. Which is actually quite strange if you think about it. Yeah? It's just like, say for example, you knock a piece of metal with a very large force, the nail goes in. The nail doesn't go in, sorry. And then you just tap, goes in. It just doesn't make sense. If you think of it that way, it just doesn't make sense at all. K of the depends also same thing. Ke doesn't depend on intensity. K depends only on frequency. You use a very, very dim blue light electron, pew! You use a red light, so it's just very intense red light somehow. So it's kind of weird. And then this one, no matter how low the intensity is, ejection is immediate. No matter how low the intensity is, no matter how low, it's immediate. You don't need to wait for light to have enough energy. You don't need to wait for the electron to collect enough energy. So that's total contradiction to the prediction. So how does light being a particle explain all these three? Which is what we're going to look at. Okay? Penetration, ionization. Someone is doing physics in this class. 3 usually. These are the 3 main ones. Yeah. Now, very importantly, when you want to create a model, light as a particle, what does it mean when we say light as a particle? What's the first question you have to answer? Mass. What's the mass? The other way of looking at mass is, what's the mass and something else is equivalent? Exactly. So light as a particle, what do we mean? It's loaded. This statement is loaded. What does it mean when we say light is a particle or light behaves as a particle? First of all, the language of physics is the energy of each particle is equals to E equals to HF. This is 6.63 times 10 to the power minus 34. This is the frequency. I don't know whether you find it amazing or not, but whenever I see this number, in fact, this is one of the smallest constants in the universe. I think it is the smallest constant, if I'm not wrong. The biggest one? Light speed. Light speed, no. Light speed only times 10 to the power 8. There's something that's times 10 to the power 23. Exactly. Mass of the universe, mass of the Earth is not constant. It actually changes with time. Molar constant, yeah, the Avogadro's number is 6 times 10 to the power 23. Anything bigger or smaller than those two? I don't remember seeing any. So the question is, how do they measure this? We'll talk about it later, yeah? How do you measure something times 10 to the power minus 34? So light as a particle means that the energy of each particle is this. Einstein wasn't again the one who came up with this. It was Planck, yes, correct. Of course, Max Planck. Max Planck. Max Planck is an Austrian? German? German, right? German. Max Planck. It's not Max Planck, it's Max Planck. Planck. Mach Planck. Okay, can. Now, how about intensity? When we look at intensity, it is energy over time area, because this is power. It's power per unit area. Don't know how much you remember about topic 4 and topic 9? The wave passed by. Passed by. Okay, so this is an important jump already. From here to here is the particle bit already. This is still light. This is still the classical physics. This is the light as a particle bit. Why? Because I interpreted energy as equals to the number of light particle times the energy of each particle. Now, why is this interesting? So when I increase the intensity of a light source, what I am doing can be two things. I can increase the frequency, or I can increase the number of particles. So if I use a very intense beam of red light, it means that each light particle has low energy. But I send in a lot of particles. Can you see that? Now if I use blue light, each particle will have more energy, but I may send in lesser. So which one do you think? Can you see now why it explains what you observe over here? If I were to send in a very intense beam of red light, basically I'm just sending in useless photons. Right? Each photon doesn't have enough energy, even though I send in a lot of them. But when I send in a very dim beam of, say, blue light, each particle has actually a lot of energy. So that's why it explains why there is a minimum frequency you need to have so that it ejects the electron. And that's why it explains why the K of the electron depends on frequency, because the energy of the photons depends on frequency. Now, last part, the third part. Why is it that it explains this? Let's take a look at some calculation. Say, for example, the power of this is, guess, make a guess. What's the power?
240 times...
make a guess.
Times...
Order of magnitude, IB syllabus.
1 times 10 to the power 3.
1 times 10 to the power 3. Kilowatts. Kilowatts, you're getting suntan already. You can take up a clothes and suntan already. No lah, kilowatts, you'll be like feeling the heat already. About 20 to 50 about there. So let's say 50 watts. 50 watts means 50 joules per second, right? Let's divide it by HF. Frequency of light, make a guess. About, say, actually it's white light, but let's assume that it is somewhere about 600 nanometers. Can someone just press the calculator?
Nanometer is now the unit of frequency.
Oh, yes, of course. Thank you for, thank you. It's 3 times 10 to the power 8 divided by 600 times 10 to the power minus 9, yeah. This is frequency now, yeah? I was thinking about wavelength. Now, can you make a quick calculation? Let's take out a calculator and make a quick calculation. How many photons are we talking about per second bombarding you? Just do a calculation. Just do a calculation. What's the order of magnitude or the number of photons we're talking about? Someone just shout out the answer to me. Sorry? I? Okay lah. Possible. I finished marking half already. I'm waiting for the other half. What's the order? 10 to the power of? How many people? Negative 30? This is negative 34 already lah. Cannot be negative 30. Sorry? 20, yeah, correct. How many people are there in the world? 7 billion? 7 billion? Let's say 8 billion. Say suddenly we become more productive. So let's throw in another billion people. So after Valentine's, probably more already. So the thing is, if you have 8 billion people, it's 8 times 10 to the power 9. 8 times 10 to the power 9. This is 10 to the power 20, okay? That's 10 to the power 10 times more than the number of people in the world. Universe don't know, probably there are more out there. But 10 to the power 9 is the number of people in this world. Or 10 to the power 10, if you say 8 is close to 10. You got 10 to the power 10 times more than the number of people in the world bombarding you every second. The number of photons bombarding you per second. Can you see that that's why even if you have very low intensity, there are a lot, gazillion amount of photons bombarding the electrons? And that's why the ejection is still immediate. Because so many photons interacting with metal, even if you have like 1 microwatts, that the ejection is immediate, so long as the photons have enough energy.
What's our area and distance?
Yep. Good point. Good point. So say for example, even if you have this and then it emits the light in 4 pi r square, and then you take your surface area. Let's say for example, the energy you receive is 1 microwatts, which is 10 to the power 7 times smaller than this. Fair enough? Then you take this divided by 10 to the power 7, you still have the 10 to the power 13. Yeah, if you have 1 nanowatts, you still have like the number of photons equivalent to the number of people in this world bombarding it per second. Which is a lot. That's why it is immediate, no matter how low the intensity is.
So what if it gets above 10 to the power negative?
Sorry? 10 to the power negative?
Because you said -7 now, right? What if it actually goes to
-7. Where did I say -7?
like nanowatts? So if it goes to like -20 watts, that's what
-20 watts. I don't think you're able to control that kind, and say that I'm able to do -20. Hypothetically speaking, if you're able to control the number of photons to that level, then you have got to wait for some time. Yeah. Can? Your IA. I don't know how you can get 10 to the power minus 10 ampere and times 10 to the power minus 10 volts. Because that will be the power. That will be 10 to the power minus 20 watts, right? I mean, you mentioned that you need to get to that point, if you can. Right? I mean, if you can actually get to the level that is low enough. Okay, honestly, I think I lost you somewhere. I think I might have misinterpreted your question somewhere. Yeah, but I don't think the experimental part of it is possible to get to that kind of energy level. But scientists have been able to eject electrons 1 at a time. They can control electrons 1 at a time to that level. They just need to ensure that the current that is what they do is that they heat up the metal, and then they measure how by varying the temperature of the metal, they can vary the amount of electrons that flows through. Yeah.
How do you measure frequency of a particle?
Frequency of particle, that's a very interesting question there. I mean, what you're asking is, take a step back. How do you visualize a particle and a wave coming together, right? Sometimes they behave as a particle, sometimes they behave as a wave. So what's the meaning of frequency in the context of a particle? That's what you're asking, am I right? Or what's the particle's frequency?
You mentioned that light is a particle, but then you use the equation.
The most commonly accepted idea is that you have this packet of wave. So what do you define as a particle? A particle is anything that has a defined start and end. So it's like a jingle in the space. The start of the jingle and the end of the jingle is that particle. That means they behave as packets of wave. Yeah? Where it has a start and end. Sorry?
Is it just electron for every single particle?
Every electron.
Is it just electron that can be seen as a small package?
In fact, that's the next part of the whole equation, that you'll find that actually electrons that we know as particles, neutrons that we know as particles, protons that we know as particles can behave as wave as well.
So we are waves.
You're a collection of waves, yes, correct. You're a constructive collection of wave. Yep. So coming back to your point, I think the most commonly accepted model is a packet of wave.
So the frequency is?
The frequency of this thing inside here. Yeah. Ken? Yeah.
So I don't really get the second part.
This one. Yeah, it's actually common. Now this is actually a general understanding of intensity, which is still true for waves. That intensity is equal to power over area. What I did over here from here to here is to interpret energy incident as number of particles times the energy of each light particle.
So what is T?
T is time, because energy per unit time is power, and intensity definition is power per unit area. Yeah? So you need to remember, what do we mean by light being a particle? This is what we mean. Now, all nice, right? Theory sounds good, right? But no proof yet. Right? Theory, oh, they're happy, oh, cannot explain that. Oh, I come up with this theory, can explain. Scientists shouldn't be happy. Hypothesis is correct. A theory. Now, theory is still a theory. It will be a dream or nightmare if your theory is not proven right. Yeah, but if your theory is proven right, then it becomes a law. Yeah, Ken. So what's the experiment done to prove this theory? Now, you can't prove a theory experimentally until you have you see, you got the theory. then you conduct experiment to prove what? To prove the theory, right? But to conduct experiment, you always have a hypothesis. Hypothesis must have things that starts with V. I mean, variables, yes, correct. You need to have variables, well-defined variables. So what Einstein came up with is it's called the Einstein equation for photoelectric effect. Is HF equals to KE max plus this thing called work function. Yeah? This is called work function. You must know the definition. It is the minimum energy to eject an electron. Minimum energy to eject an electron. This is the maximum KE of ejected electron. Now, how come there's a minimum energy to eject the electron? And why is there maximum energy?
So are you saying on the left side of the equation is describing photon? On
Yes,
the
correct.
right side is
The material and the ejected electron. Yes, correct. Energy conservation, basically. Yeah. Now, the reason why there's a minimum energy is because electrons can be ejected from the surface all the way deeper in. So those electrons deeper in will require more energy to eject, and that's why the K will be lesser.
But there's
Yeah.
no thermal energy or anything because
That's why it has to be, actually the proper definition is, photoelectric effect is the ejection of electrons from a cool metal surface. Cool metal surface. That's why it's not by thermal agitation.
but it doesn't get heated up by the light shining.
It does, so long as you, I think the temperature rise, if you were to use this kind of, it will have reached thermal equilibrium, right? It will have reached thermal equilibrium. Yeah. Ken, so this is the equation that governs. And how do they prove it? How do you prove the equation? This is a constant. You need to have the variables, right? So what they do is that they rearrange the equation K max equals to HF minus work function, and then they plotted K max of the ejected electrons against frequency, and the graph looks like this.
So it's a proof.
Yes. It's proven that the equation is correct, therefore the theory on which the equation is built on is correct. Yes, and therefore, hang on, can you see that the gradient of the graph gives you the?
H function.
Yes, correct, and the y-intercept over here is the work function, correct, of the material. And hang on, just give me now if I repeat the experiment with different metals, then you will have the same gradient, but different y-intercept because they have different work function. The gradient must be the same because it is Planck constant. Ken? Yeah. Your question.
So is it reversible? So
Reversible meaning?
if I use photons to impact on a metal surface,
Then if you push electrons onto the metal surface, yes, that's an excellent question. In fact, that's how you actually find discoveries, opportunities for discovery. X-ray, that's basically X-ray you're talking about. If you throw electrons with high energy onto metal surfaces, you will have X-ray coming out of the surface. But sometimes it's not reversible. Sometimes it's not reversible. Yeah. Sometimes it works this way, sometimes it works both ways. Not all the phenomena works both ways. Yeah?
and then for this, because it's governed by the equation, using the equation, how that actually.
Yep. But let me give you an example. Like you don't throw electrons in and you see visible light coming out. Yeah, you only see if high enough, and the interaction is another form of interaction. It's interaction with the nucleus. It's not interaction with the atoms. But generally, the idea of throwing light and then EM radiation and then electrons out, when you throw electrons, EM radiation come out is true. Can? But it's not the same mechanism. Yeah. Cool, Ken? So, one question for you to think about. You must remember this is 100 years ago. How do they measure the frequency? So question number two. Question number two. How do they measure K max of electron? What time the electron? Bang! Bang! How do you measure? Wavelength is still easy. Wavelength, you know Young's double-slit experiment? Can measure the wavelength and therefore the frequency. Yeah, that one measurable. Measurable. Yeah, but how about K of electron? How can that be done? You're throwing fragments and not methods. Okay, this is exactly what was being done. I mean, in a nutshell, I mean, this is yes, micro emitter. In fact, sometimes you have to use nano emitter. This is really smart. This is really ingenious. They shine the light, electrons get ejected out. It goes this way. So if this is a variable EMF source. If I put this negative and this is positive, can you see that at some point the electrons ejected out will be repelled strong enough such that the most energetic electron will come to rest right in front over here. Okay, if I make this negative enough, the electron will face enough repulsion to stop right in front of here. Make sense? Now, then if I have Ke max over here, what happens to the Ke max over here when it comes to here? Energy is destroyed. Converted to what? No, it comes right before. It doesn't even touch here. Why would that be heat? The electrons become hot. Hot electrons. Hot electrons. The same thing. You know, in primary school, we ask students what happens when you heat up a piece of metal, the atom expands. The metal expands. Yeah. So what? This gets converted to? Come on, topic 5. Topic 10. Electric potential energy, correct. So it's Q delta V. Now, how do you find delta V? Q is known already at that point of time, 1.6 times 10 to the power minus 11. How do you find delta V? Exactly. Exactly. So what you do is that you just vary this until no current appears here. Sorry? No need. That's why I put it as the last. No need. But you guys are ASP people. I'm sure you're very keen. In the midst of your IA, you still want to know more. Yep. Well, so how does that allow you to find Ke max? Oh, but hang on this one. The experimental method you don't need. Experimental method don't need. Yeah, but this one you need to do. Yeah. Max deviation. What do you mean by max deviation? Quantify.
So for example, right, the electron is let into an electric field,
Mm-hmm.
the detector,
Mm-hmm.
you know the ones that we use in our math application. So electron detector.
Oh, okay. Understand what you're trying to say. So basically, you have an electron entering here, and then the magnetic field. Let's try this. I mean, mv squared upon r equals to bqv. That's your topic 5, right? So boom boom, and then your momentum equals to bqr, or r equals to p upon bq. I got a feeling that this is going to be too small because the momentum of electrons are generally very small. And the electrons get ejected in all directions. So it's going to be very unwieldy for you to control the movement of the electron. Plus, the momentum of electron is really small. Why? Because the mass is minus 31. Yeah? And then you multiply by even speed of light, 10 to the power 8, you still got minus 23. And then you divide by this one, minus 19 is still 10 to the power minus 4. So it's going to be really small. You're talking about millimeter range. Uncertainty is going to be really high. Yeah, and electrons get ejected over here in all directions. Yep.
How do you know that the electron?
But it's a good idea.
Electron that hit the negative terminal at the maximum thing.
Okay, because when you increase the negative potential over here, the number of electrons, because the electrons are ejected with a range of energy. So when you have, let's say, minus 1 volt, the smaller energy particles will be repelled already. So your current over here will start to fall immediately once you put. You continuously increase it, minus 1, minus 2, minus 3, until no current is detected. Meaning that the most energetic electron will have been stopped already. So that sets the upper limit. Okay? Smart, right? Elegant, I mean, simple method. You convert something that's so invisible, Ke of electron, to a visible, measurable quantity over here. That's how smart the experimental scientists are. I mean, they convert difficult to measure stuff into measurables. Yeah, okay. So that's it for photoelectric effect. That's the interesting part. That's half of the equation. Light, which is a wave, behave as a particle. Now that's the other part of it. I'm going to go through the other part already, where particles can behave as wave. Yeah. Let me finish that, and then I think you look like you have enough particles coming up from your brain already. Yeah, I think it's enough for the day once I finish the particle behaving as wave. Now let me show you an experiment which scientists did, and it gives very, very interesting results. Now what scientists did was the Young's double-slit experiment They threw wave at it. Come on, you should know what is observed over here. You should know how to come up with the equation, and you should know how to draw the intensity pattern. So, what do you see? What do you see? Yeah, correct. Agree or not? Now, what are these called? They're called what? It starts with F. Ferns. Ferns. Oh dear. They're called ferns. Fringes. Yes, correct. Fur. Furry. Okay. In the fringes Now, what is interesting is they throw electrons. Electrons at this after a long period of time, if they put a photographic plate over here, electrons expose a photographic plate. They also find the kind of very faint but can be seen one. It's faint, but you can see gathering of bands of spots of electrons. So what does it show? That means electron must be, this is deduction. Whatever you throw here, forms here, means interference occurred. Interference occurred means that whatever you throw here must be a wave. Same thing. Since you observe the same thing, whatever you throw here must be a wave. Exactly. So what on earth are electrons and particles doing? I mean, we know them as particles and then they collide. I mean, conservation momentum collision experiments show that they are particles. Then here you are, you throw electrons one at a time and then it shows that it's a wave. And then what do we mean when we say particle behave as a wave? You know, there are a lot of unanswered questions. What exactly does it mean if you can have a microscope which is ironic, which is oxymoronic, if we can see electron, which is difficult to see, impossible to see, what will we actually see? A wiggly or particle? A billiard ball or wiggly?
Is it string?
That's one of the theory. Yes, correct. That means everything in this world is yes. That means you're just one big blob of entangled strings. So when someone say that your mind is like a messed up spaghetti, yes, actually it's correct. You should say yes, correct. My mind is a messed up spaghetti of strings. Okay. Yeah. So you must imagine how interesting. No. Hang on. Before you think that you know, let's think about this way. What scientists did was they placed two detectors over here. Yeah. So what happened is that in order for this pattern to appear, the electron must have somehow split into these two, which means that there must be existence over here, right? Both at the same time. But when they put a detector there, they only detect one of them. Now, why is this interesting? Now, if you think this is interesting, it is not. This is not the end of the interesting part. The interesting part is this. The electron, after passing through here, right, it should have decided that it's a wave already, right? It passed through already, right? Then suddenly you see the detector, oops. Then it U-turns backward in time and go through only one of them. Okay, observation says that if you put a detector here, you either detect here or here. This is detected thing, observed. Which means that the electron, which has already passed through, because if you don't have the detector here, it passed through, interfere, and you see the pattern, which means that the electron might have split over here and exists on both sides. It must have, otherwise you cannot form this pattern. One slit, you cannot form this pattern. You must have two electrons coming out over here, interacting with each other. So over here, somehow, the electron realizes that it's being spied on, doesn't like to be spied on, goes back in time, and only takes one route. So which means that electron can travel backwards in time. Or the electron exists in this fuzzy region over here. The electron is somewhere there, somewhere. like you're here, but your mind can be somewhere. Your existence can be somewhere.
So is it possible for the electron to travel through like both of the holes, then it get combined quickly, they pass through the detector? So that's why only one detector detects.
So they combine quickly. Now the same thing happens to test your hypothesis, if we push it back further, then you start to see differences, right? Then you start to see one or two. But that's not what they observe. Whatever distance they put the two detectors, they always detect either one or the other one. Yeah. Which is weird. So we think we know about electrons. In fact, electrons is one of the particles that we know very little about. What exactly is electron? In fact, up till now, right, there's no known size for an electron. There's no known size. Neutron and proton 10 to the power minus 50 meters, well established. Electron, no known size. So that's why electron up till now is still known as a point charge.
So,
Yeah.
why do we pass an electron through, not a proton?
The same thing. If you pass a proton through, you still see this. The reason is because, okay, allow me at this point of time to bring in the de Broglie hypothesis. Yeah, de Broglie hypothesis. This is in your notes. It's pronounced as de Broglie hypothesis, just like Mach-Planck. Mach-Planck. It's not de broccoli, de broccoli, de broccoli. The broccoli is the one that the broccoli is the one. It is de Broglie hypothesis. Yeah. So what is so powerful about this equation is that it links a particle quantity to a wave quantity. Now, answering your question, back to your question, why don't they use proton? Can. It's just that it poses a difficulty. Because the momentum of proton is much bigger. Why? Because the mass of protons are much bigger. So momentum much bigger. Wavelength is going to be much smaller. So the problem it poses is that if you want to find delta x, when this is very small, they tend to clump together. It's very difficult for you to observe that space, that fringes. Yeah, it's going to be like there together. Yeah, so that's the reason why. Not that it doesn't. If you have a momentum that is small enough for proton, then you can actually observe that thing over there.
So is that all particles will undergo this?
All particles. Even if you run on the running track, you are running actually like this. Technically, you do behave as wave. Because this is m times v. But why don't you observe yourself as going like this? Because this is 10 to the power minus 34, your mass is about 40 kg, and then times the velocity. If you run like Usain Bolt, your speed will be 40 meters per 40. Oh no, not 40. 10 meters per second. 10 meters per second. So this is for about 500, 10 to the power 2. This is going to be 10 to the power minus 32 meters. Your wavelength is going to be 10 to the power minus 32 meters. That's why you can't see anything. But for electrons with momentum 10 to the power minus 23, that's when the wavelength is 10 to the power minus 11, which is about the size of the atom spacing.
So the real question is that when we're standing still, is it still?
Actually, we do that. According to uncertainty principle, actually, every second, the electron beside you is like. Sorry?
There's a chance that you phase 2 matter.
Yeah, I think you watched a little bit too much of X-Men. Technically speaking, there's uncertainty principle. Technically, I mean, you can jump the moon. You can jump and then you probably suddenly appear in the moon. Technically. Anything that's impossible in the quantum realm is possible. And you may think that this is sci-fi. Actually, it's not. Alpha beta decay is actually as a result of tunneling. Yeah. If you think carefully, right, electron produced in the nucleus, beta decay. Electron produced in the nucleus, right? Do you agree that the electron will be very close to the nucleus and it should have never enough energy to eject out? 10 to the power minus 50 meters is very close to the nucleus, electron. It should never escape, but it escaped because of quantum tunneling. Quantum tunneling, it somehow can jump across. Yeah. Somehow it just jump across. Yeah. Yeah, somehow. It's just like you don't have enough money to buy a ticket. Suddenly you have the ticket already. Yeah. This is weird, yeah. But in the quantum realm, this is what happens. I'll explain a little bit more later on about quantum tunneling. But at this point of time, what I need you to know is this equation. Know why, this equation. Know why is it that you don't exist wave phenomena because your wavelength is too small. Why does it only happen for electrons? Because the momentum is small enough for the wavelength to be of comparable size to the atoms. That's why you see wave phenomena when you throw electrons at crystals. Yeah, that's when you see the diffraction happening. Because comparable size. Wavelength and the size of the atoms. Okay? Now, one of the very popular equations that they'll come up with, they'll ask you to use is this. Wavelength equals to h upon p. Now, do you agree that just now we saw this equation used for photoelectric effect? It's used to stop electrons. But similarly, I can use this to accelerate electrons. So electrons can get pulled over. So the K of the electron at the end of this journey is equals to the charge of electron times the accelerating potential. Just now we do the reverse. Yeah? So Ke, I'm not sure whether you remember this equation. This is P squared by 2m. So P equals to square root 2mq delta V. You plonk this in, it will give you this very popular equation to be asked. Why? Because whenever we talk about electrons, we always talk about accelerating them using potential difference. Yeah, so that's why this is usually used, because that gives you, this is how we accelerate electrons and this is how we calculate the wavelength. Can? Yeah. If you think about this, it's actually really, it's a very bizarre world. In the macroscopic scale, you have you, me existing, but in the microscopic scale, there's so much of madness at the microscopic scale. Literally madness. Sun, yes, actually.
Like
Yes.
accelerating electrons.
Accelerating electrons, protons, wave nature of particles, the hadrons, mesons, all these things.
Yes, sir. You
Yeah.
know the batch below us, they're going to serve.
I never talk about that. I didn't even talk about it. If you remember my ASP talk to you, I also didn't mention anything about it. Yeah. I had to delete the slide away. Okay, it's okay, it's okay. You can always go to CERN's website.
No,
You can always go to CERN's website.
You can always work at CERN.
Yeah. Okay, anyway. So, in a nutshell, today we have covered the big portions, the big giants of 12.1. The next 4 subtopics, which is conservation of angular momentum, pair production, uncertainty principle, wave function, tunneling. I can finish it in probably 2/3 the time that I spent today. Smaller sections. Today is a big giant. How light behave as a particle, how particle behave as a wave. That's basically the wave particle duality. Yeah, wave the okay, can. Relax. And that's it for today. I think we have enough for today. Can you stop the recording? Thank you.